About Amdahl's law. I briefly mentioned that in the class, but since we ran out of time, I thought I'll do a small video on it and walk you through a few examples to show how Amdahl's law work. So let's quickly remind ourselves about the multi-core architecture, where we saw there are multiple cores and multiple tasks can be launched on these cores, so that all of these tasks make simultaneous progress. We also saw how we went from one core where one process would monopolize all the system resources and use the CPU core. But now, as the architecture and hardware is becoming more sophisticated, not only the applications have become parallel, but the OS operating system has also become multi-threaded. That means there are kernels, kernel threads, multiple kernel threads at the OS level, and there are multiple user threads that take advantage of those and run multiple tasks at the same time. So next I want to show you Amdahl's law that identifies the potential gain from adding multiple cores to an application. So in specific, it talks about applications where you have both parallel and non-parallel parts. So in an application, for example, the example that I talked about in the class was where you could parallelize a for loop, for example, in an application. For example, your for loop does you could say vector addition, and you parallelize that so that you're performing vector addition over multiple cores, and then rest part of your application is still serial. That means you're going to be working on one core, and then single instruction, single processing type of model. But you also, part of that application is also parallel, where you can take that particular for loop and launch it on multiple processing cores. In that case, we are interested in knowing what was the speed up of that application. So in that case, what we're going to do is we're going to look at the non-parallel part, which is the serial part, and then we're going to look at the non-serial part that was parallelized over multiple cores, and those multiple cores are denoted by number n. So n could be 2, n could be 3, and so on. So 1 over s, that is the percentage of your code which is serial, that is executed on one core at a time, and then there's this part of your code that leverages multiple cores of the system and then runs your code parallelly. So the sum of those divided by 1 over sum of these two items gives you the speed up. So here there's an example. They say, suppose there's an application where 75% of the code can be parallelized and 25% in serial. In this case, what would be the speed up of your code using two processing units? So let's try to work on this example using the same formula. So I'm gonna pick a pen, and speed up is 1 over s. S in this case is 25, which is the serial part, and the parallel part of your application is 75, and you have the number of cores to be 2. This is 37.5, and this comes out to be 62.5, which is, I'm gonna have to use the calculator here. 62.5, so that's 0.016 in percentage. That would be 1.6% speed up, or times. So this would mean 1.6% or 1%, 1.6 times, let's say times speed up. So if you parallelize 75% of your code and run that over two cores, you would gain 1.6% speed up. That means your application is now faster. Now the second part of this, so that's what we saw here. That was what we also got. So they say, what if we add 2 additional cores? Now we have a total of 4, that means, let's see, if you have 4, this part becomes 75 over 4 is 18.75, and which comes out to be 43.75. And let's quickly do a division. Obviously this is not the case anymore. Let's do a division again. 1 over 43.75 is 0.228, so if you round it up, it comes out to be 2.29 times. So you're going to multiply that by 100 because all of this is in percentage, so that's why I'm multiplying this by 100. And then this becomes 2.29. Let's verify our answer. Okay, they didn't round it up, so okay, this is a 5, so it won't round up to 9, so the answer is 2.28 and not 2.29. Let me fix that quickly. 2.28 is the speed up. So hopefully this was easy to follow. Let me also do one more example from end of chapter. There is one problem where we have to apply Amdahl's law and calculate the speed up. Here it is. It says, use Amdahl's law, compute the speed up gain of an application that had 60% parallel component with 2 processing cores and 4 processing cores. Let's do one of them and then I'll let you work on the second one since you've already seen the pattern. So here, let's erase all of this. Here you have 60% of your code that's parallel. So what that means is 40% of your code is still serial, and you have 2 cores to start with, which makes it 1 over 70. And to save us some time, I've already done the computation. Comes out to be 1.43. And if you also want to see what would be the answer to the second part, you just gotta replace this with 4, and this would be 40 plus 15, this would be 55, and 1 over 55 is 1.82. So in that case, your speed up would be 1.82. So these are the 2 speed ups that you would have when you have 60% of your code that's parallel and 40%, the remaining percentage, is still serial code. So hopefully you got some idea what Amdahl's law is and how to compute speed up. I'll stop the video here, and if you have any questions, we'll discuss them offline. Thank you for watching.